introduction and for the invitation to come here. I don't know what is happening now. Yes, it's coming. Yes, good. Yeah, so it's a pleasure to have Jens as a chairman, my honor. And so, well, yes, in a way, I see that some of the things I'm going to say from a different perspective are connected to the previous talk. So what I want to tell you is something, I don't know what happens. Let me see. Yes. Okay, yes, a bit. Yes. Okay, good. So I will focus on, let's say, more standard many-body physics, okay? And, well, more standard, or many-body physics, let's say. So I think we all agree that now there are efforts to understand how the physics of many-body systems, no, from a theoretical and experimental point of view. So there are many questions, like you may know, like, okay, you have a Hamiltonian, you want to find the ground state, and then understand the properties of the ground state, like phase diagram. Or you have an open system dynamics and you want to understand the properties of the steady state. Or perhaps the hardest is like you are a Hamiltonian or open system dynamics and you want to understand the evolution of the many-body system. Okay, so these are paradigmatic problems that I believe I don't need to introduce. Many of you are familiar with, or basically all of you are familiar with these problems. So I will be focusing on these problems, and I think this is why it connects with the previous talks. I think we are facing an interesting problem in which we are interested in problems, and we know that by construction, somehow the full characterization of your system requires a number of parameters that grows exponentially with the number of particles. Okay, this is a fact because you have a large Hilbert space and you need an exponential number of parameters. But we know that whatever you do, I mean, what you can measure, this is what also connects with what Jens was saying, like you're never going to measure an exponentially growing number of parameters, right? You're going to measure a subset of those parameters. Or if you want to make computations with this state, you are never going to store an exponentially growing number of parameters on your computer. Okay, so by definition, you cannot do these things. And I think somehow you may even question what is the, I mean, on the ontological discussion, no? What is the reality? Is this one or this one? Okay, so I think we are somehow facing this nice observation, no? And what is a fact, independently of ontology, is that we have to learn how to deal with partial information because we will never have access to what is in principle needed to have a full description of your system. Okay, so this is my talk. I'm going to understand how you can deal with this fact that in theory you need this number of parameters. In practice, you can have access by experiments or even by your computation capabilities to a much smaller number of parameters, and you have to make useful predictions about your system from this limited partial information. Okay, maybe this is not partial information. Maybe this is full information, and this is over information. Okay, but okay, this is more philosophy. We can have a beer and discuss about these things. Okay, so I will represent what I wanted to tell you with this paradigmatic problem. So you want to understand the ground state of a many-body system. So again, what does it mean that you want to obtain the ground state? You cannot even store it. You cannot even write the vector with all the exponentially growing number of parameters. Okay, so basically, I would say, okay, what you want is you want to understand the physics of the ground state, which probably means I don't want all the 2 to the n coefficients of my ground state. I will want to understand a subset of the properties of the ground state because I'm physically interested on these properties. I think that they are relevant for my experimental situation. So just to illustrate this, imagine you want to understand the magnetization of your ground state for a many-body system. So what am I talking about here? The formulation. So you fix the number of particles and you have a Hamiltonian, and then there will be a ground state for this Hamiltonian, and you want to compute the expectation value of the property of interest. In this case, I took magnetization on the ground state. So what do we need to do? Well, in principle, it's clear. We have to find the state of minimal energy. So okay, this is the state that solves this problem, and then simply compute the expectation value of these observables on this state. Okay, this is all what we need to do. So how do we deal with this? Well, you do exactly what I just said. You solve this exactly. Okay, what is the nice things about this exact result? Well, of course, you get the right result, okay, because it's exact. What is the problem is that you don't go very far with this because, as I was saying, things go exponentially with the size of the system. So you will reach this for 40 qubits, 50, I don't know. Well, it depends on how much money you invested on your computer, but you won't go very far. So what people usually do is like, okay, people accept that this cannot be solved exactly. So what people do then is like, okay, I'm not going to do this over all possible states. I'm going to do the minimization over a subset of the states. Why? Well, sometimes this is based on physical considerations. Like, for instance, if you study 1D system and the system is gapped, then you know that this will be described by a matrix product state of efficient bond dimension. But sometimes, in some cases, people take these answer states simply because they can compute things, okay? So, and then you hope that potentially this is good. So then what people do is like they restrict this search over a set of answer states. They solve, because then they can compute things, they can compute this, they can minimize it. There might be local minima, but okay, they can do something for large sizes, very large sizes in some cases. Then they get the ground state, and they compute the ground state magnetization, okay? But they don't have any guarantee with this. I mean, they don't know, for instance, okay, you have this variational method that looks, okay, if this is the ground state, you don't know if you are close or far from your actual ground state, okay? I mean, I think here no one will complain with that. Sometimes when I give this talk, I have to say variational methods are very successful. Okay, I don't have anything against variational methods, but it is a fact that you don't have control about how close this number is to that number. Or what you can say is that this is an upper bound to the ground state energy because, of course, this is a possible solution to this is all what you can say with rigor about your system. Okay, so to summarize, I'm being a bit brutal. You can say that there are two approaches. The one is exact. Nice, you get certified results, actually exact, but you don't scale. Variationals, you scale very well, but you have no control about how close you are. So what I wanted to tell you the story is that I think polynomial optimization methods, they give you some, okay, you will see things are nice, maybe not as nice as it seems here, but they give you ways of getting certified results in a scalable way. This is a fact, okay? So and there are several people working on that. I put this because maybe it's one of the first papers we did in the group, together with the group of Victor Magron in Toulouse. And this is what I'm going to tell you about. Okay, so somehow you can have a different way of approaching these problems, which is using these polynomial optimization methods in which you get good properties from the previous instances. There are still challenges, and the problem is hard. Well, we know that many of these problems in general are hard. Okay, so of course this is not going to solve all these problems in full generality, but I think it's an alternative that deserves to be explored. This is basically the message I wanted to give you. Okay, so because also second message is like, I want to tell you that we know that we are dealing with, in general, with these complex problems. We need many parameters, they are hard. And the recipe I'm going to tell you to face a complex optimization problem is that I'm going to suggest you to relax, okay? So you take things, you sit down and you relax. And what I mean by relaxing, I mean that I suggest you to apply this non-relaxing combination of terms, which is the hierarchy of semi-definite programs to solve polynomial optimization problems. Okay, so it's very scaring in a way, but it's a relaxation, you will see. Okay, so now what I'm going to do, I'm going to tell you a bit of the ingredients that appear here very quickly and in a qualitative way. So what is polynomial optimization? Well, this is rather simple to introduce. I think you have seen polynomial optimization problems. I will do it first in the classical case. So you have a polynomial depending on some variables, and you want to find the minimum, okay? You want to optimize the value of this polynomial over these n variables. And you also have some polynomial constraints, so that I give in these positivity conditions. Okay, equalities you can always see as inequalities. And you can always phrase equalities with inequalities. So basically you have m polynomials on the same variables positivity. So this is an instance of polynomial optimization in the classical case. So for instance, if you want to have, well, this is an instance of polynomial optimization, okay? So you want to find the solution to this quantity. Now, this is usually hard, and okay, you have to understand what is going to happen. I represent by this gamma bar the set of points of Rn in Rn. Okay, this is now, the screen is Rn, okay, it's an oversimplification. And then the set of points that satisfy these constraints, this is a set of feasible points. I represent by this gamma bar. I put it convex, but it's not going to be convex. It's simply because I was lazy when making the figure, okay? But this is the set of feasible points, and this is the polynomial, okay? And now in this figure, what is the solution you are looking for? Not this one, of course, it's that one. Yes, this is the minimum in the set of feasible regions. Okay, this is the problem we want to solve. That might be hard. So what you can do is something that was introduced by Lasserre, and also Parillo was working on that. So they say that the following, some of the idea is like, okay, some of the problem is, one of the reasons why it's hard is because it's hard to characterize the region of the feasible region. So what I'm going to do, I'm not going to work with the feasible region. I'm going to replace it by another set of points that contains the initial set, but it might be larger. But the good thing is that this minimization now becomes easy. In fact, becomes an instance of semi-definite programming that I can solve. So what this means is that instead of solving this problem, the original problem, I replace by these outer approximations to the set of feasible points, okay, this gamma case. And instead of solving the minimum over this region, I solve it over these outer approximations. If you look at the minimization over an outer set, you will get a lower bound to the solution. Okay, so this is what they did. And what they prove is that so you have a hierarchy of tests. So basically, each instance is computationally more demanding. And what they prove is that under some mild conditions, these outer approximations converge asymptotically to the set of interest. And so you have a sequence of lower bounds that converges to the minimum of interest. I hope everything is clear here, because this is quite critical for my talk. Okay, so you approximate from the outside and you get lower bounds to the minimum. Or if you maximize, you will get upper bounds to the maximum. Okay, so you can use it, for instance, in the many-body context, and people have been using these things. For instance, you have a classical spin system and you want to find the ground state energy of the classical spin system. Well, this is nothing but an instance of polynomial optimization, right? Because you have here, the variables are now the spins, okay? And the spins are equal to plus and minus 1, and this is again a polynomial constraint. And then you can use this, for instance, to get lower bounds to the ground state energy of this system. Okay, so you can solve this classical spin system with Monte Carlo. And now you can use this, and you will get lower bounds, and at least you have some control about where the ground state is, because you have an energy window in which the ground state is, okay? So you have some control about, you may even use it to have some control about how close your Monte Carlo solution is. These methods don't scale as well as Monte Carlo, okay? But in principle, you could use it to get lower bounds. Okay, so I'm going to focus on quantum systems. So, and here I will introduce somehow the non-commutative analog of what I was telling you before. So basically, we want to solve a polynomial problem now over non-commuting operators, because in quantum physics, we are dealing with vectors and with matrices, no? Hamiltonians are defined by operators. So we have a polynomial over some operators, and I want to find the minimum eigenvalue under some conditions on these operators that have a polynomial form. So I basically did the same as before, but I'm replacing commutative variables by non-commutative variables. And together with Miguel, who is sitting here, and Stefano Pironio, we found some years ago a way of doing basically the same, okay? So we found outer approximations to the set of feasible solutions that asymptotically converge, and then they give you lower bounds to the minimum you are interested in. So it's basically the same idea. It's funny because we were not aware of these things, of the classical result. We found some construction in a problem, and then we realized that what we were doing was the non-commutative analog of what people had been doing in a classical optimization. Okay, so but it's basically, I don't have time to go through the details, but you can do these things, and the nice thing is that each computation is semi-definite programming, so you can do it if the matrices involved are not too large, you can do it on your computer. Okay, so now let's see what happens for quantum models. So you can also apply these techniques for quantum models. So now you will have, now I take the same notation, but you have to understand that now these are spin operators. They can be, say, sigma x, sigma y, and sigma z, okay? And okay, so you apply this machinery and you will get lower bounds to the ground state energy that converge. So I want you to understand what is happening here. Also, now maybe I will get closer to what is happening in the method, okay? So in principle, you want to solve this problem. You want to minimize the expectation value of your state with the Hamiltonian, okay? So now you can put the state with each term. I'm just taking a rather standard Hamiltonian made of two-body and one-body operators. This is more physical, I would say. Okay, so basically what you have to solve this minimization, okay? So if you look at this, you say, well, why is this difficult? I only have to optimize over some expectation values. I don't have many. I mean, if this is linear or square, you have a polynomial number. So it doesn't look so difficult. So why is this problem difficult? Well, the problem is difficult because characterizing, if you put it in this form, this is just a linear combination of these numbers, which are expectation values, okay, the quantum expectation values. So the problem is difficult because characterizing these quantum expectation values is difficult. Okay? Finding expectation values for two body and one body Paulis that come from an n-party state is difficult. Okay? Because if this set was easy to characterize, this would be a very simple problem. Okay? You only have to combine a linear combination of these numbers. So the only reason why this is difficult is because this set is hard to characterize. Okay, so again, this is what I'm just rewriting. Okay, you have to optimize this linear combination of these numbers. Okay, but I have to characterize these quantum numbers, these quantum expectation values. I'm going to call these quantum moments. So basically, what this method that we introduced does is like, okay, I'm not going to do this. I'm going to do it over a set of expectation values of moments that contains the set of quantum moments. Okay, it's an outer approximation to the set of quantum moments. It's always the same. I take the set of physical objects and I replace it by another set that contains the set of physical objects. Okay, so you want to understand here pictorially, I want to solve this problem over those numbers here that have a quantum representation. I don't do that because I don't know how to do it. I do it over an outer set that I call a set of relaxed or larger expectation values. I'm not telling you how we do it, but or how you can do it, but believe me, you can do it, and this is what you do. Okay, you take an outer approximation to the set of physical states. So you want to understand a bit the things I've been discussing. Variational methods, what they do. Okay, in principle, in the problem we want to solve, we want to characterize this set of quantum moments, of quantum expectation values, because what we are interested in is in the value of a linear combination of these quantum moments. Okay. And variational methods take a subset of quantum moments that is non-convex in general, and they find a solution. They may get a local minima, but okay, I take the best. And what you do in the non-commutative polynomial optimization, you take an outer approximation. So in one case, you get an upper bound to the ground state energy. In another case, you get a lower bound. And you hope that these numbers are close to the number of interest. And in particular, quantities that you later compute, like magnetization, are also close to the magnetization of this state. Okay, so these are some of the approaches that exist. Okay, so I will now tell you about the first paper on this certification. So again, after this introduction of some of the main ideas we are going to use, the problem I want to solve is what I was telling you, right? So you have a Hamiltonian, you want to compute the ground state energy. You want to derive the ground state, which is the state that gives the minimum energy, but you don't want the energy, you want to understand a property, say magnetization, either described by an observable. And you can do it, as I was telling you, in an exact way or through variational methods. You can also use the polynomial optimization and you get not an upper bound and a lower bound, and even some sort of estimation of this property. But again, all what you can certify in the variational method is that an upper bound the energy, and with relaxation a lower bound. About all what you estimate here, you have no control about how close they are. Okay, this is some of what the situation, I would say, before the paper I wanted to tell you about. Okay, so what we realized in this paper is that something that you can do is that if you put the two things together, you can get certified bounds on any quantity of interest in the ground state. Okay, so I can tell you, I cannot solve the problem exactly, but I can tell you, look, magnetization is between this number and this number, and this is a rigorous bound. Okay, actually what we need from variational method is nothing but the upper bound on the ground state energy. Okay, maybe you can use more, but in this paper, we just need to know an upper bound on the ground state energy, and then I take all the structure that we had on polynomial optimization, I put the two things together, and I can tell you bounds, lower and upper bounds on quantity of interest at the ground state. So how does it go? If you understood what I was telling you about these quantum moments, okay, this is the problem, the ground state problem that I have been discussing, okay? So you have this optimization of the Hamiltonian, okay, over these quantum moments. This is the ground state problem, okay? And what I did, I was replacing this by this outer approximation to the set of quantum moments. So you may say, wait, I mean, if I think about a system of n qubits, it's not the Hamiltonian that is a function of Paulis, but any observable is a function of Paulis, okay? For instance, magnetization in the z direction is the sum of sigma z for each Pauli. Okay, so it's just a polynomial. So I can always express any polynomial as a any operator as a polynomial of Pauli's. So maybe take the polynomial you are interested in and do the same as I was doing here. Instead of for the energy, you're doing for the magnetization. Okay? Well, if you do that for magnetization here, you will get the magnetization is bounded between -1 and +1, because I'm not demanding anything from the state. I just want to optimize magnetization in an n-qubit state. Okay, I will get -1 and +1. So here is where you use the information you got from the variational method, because you are not interested on magnetization everywhere. You are interested in magnetization of the ground state. And you know that the ground state has an energy smaller than the value you derive with the variational method. So you include this extra piece of information in your optimization problem. And everything is polynomial, so all the machinery of polynomial optimization can be applied to this. Okay, so I do this. It's basically the same. I replace the Hamiltonian by another combination of Pauli's. I have the same constraints as before. I add the extra piece of information coming from the variational method that the energy cannot be larger than the upper bound I derive. So, and with this, now, if you understood what I'm doing, okay, so this is what I have to do. I have to do it over the set of quantum moments. Okay, I put the variational method. I relax. I compute the minimum. I relax it. I get a lower bound. I compute the maximum. I will get an upper bound. Okay, so with these things, I can tell you the magnetization is between a number and another number. And I can do it for any observable interest. Okay, it has to be written in a non-crazy way in terms of the Pauli's. Okay, but you can do it for any quantity of interest. Now, does it work? Okay, because I mean, getting bounds on magnetization, I can give you a bound, -1 and 1. It's a rigorous bound. Okay, so they have to be informative. Well, I mean, for sure, in general, there will be, these problems are NP-hard, no? So there will be an instance where things will go wrong, okay? But, okay, wanted to see in practice if they work well or not, okay? So what we did, we took, as a representative in that paper, we took a standard model that is called a Heisenberg. So you have XX, YY, ZZ in a 1D system, in a 2D system. And, oh, sorry. And also we took another one, which is with nearest neighbors and next to nearest neighbor Hamiltonian. Okay, so we took different models in 1D and 2D configurations. So the first thing we did was, let's see how all this non-competitive polynomial optimization determine the energy. Okay, you can, in here you should forget about this orange line. So you don't see it here, but there is superimposed the upper bound on the ground state energy and the lower bound. Okay, so I can tell you that the energy is between, I don't know, like 0.4448 and 0.4449. Okay, so basically, I'm sorry. Okay, this is what I'm telling you here, and this is for this 1D with this extra term. You see the upper and lower bound. If you see lower bound, DMRG, well, they are very close. Okay, so here I can certify the value within a very small energy range of the ground state energy. Okay, this is something that you cannot do by variational methods alone. But perhaps the most interesting thing is going beyond energy, okay? So for instance, this is, we took, okay, it was like playing a bit, okay? We took two-body correlation functions, and this is what we were getting, okay? So in this case, it's a 1D system. Probably the MRG is giving us the ground state. You never know, but probably it is, okay? And we were computing the upper and the lower bound, and well, you see now, I can tell you that, I don't know, the value of this two-body correlation function is between these two numbers with certainty. And okay, we're playing a bit. So for instance, here there is something interesting. Sometimes the value, I think also we should understand what we are interested in. Am I interested in knowing a two-body correlation function is equal to 0.3789? No, maybe not, okay? So maybe I'm more interested in the physics, whether something is positive, negative, whether spins are aligned, anti-aligned. This is usually quantities of more interest. So here, for instance, I can tell you that in this case, this two-body correlation function, I can certify to you that it changes sign here, okay? Because here the lower bound is positive and here the upper bound is negative. So I can tell you the ground state has a change in the value of this two-body correlation function. I can certify to you. Sure, the DMRG tells you the same, okay? But again, you should never trust the result. Or you can trust it, but with some caution. And then we went to two-body models. Okay, here things are, okay, is it good or bad? Okay, you tell me, okay? So this was the result for Monte Carlo for the energy. This was the lower bound. I think the difference is okay, but I don't know. Depends on you. And also we took some other situations. Okay, we were getting, maybe, let me go here. Okay, we had larger gaps between the upper and lower bounds. Large, small, I don't know. Okay, so we can always give these certificates about how of the physics of the ground states. Here you see, again, a gap, but I can tell you that here it goes from positive to negative. So if this is another parameter, I can tell you there is a phase transition somewhere here, there. Okay. Okay, so I think there is work in progress on that, okay? And what we also realize is that, how am I doing with time? I'm about 0, no?
Minus 35.
Okay, so, okay. So what we realize is that the same thing you can apply to open quantum systems, okay? So I will go quickly then. So basically you have now, it's a different problem. You have a system interacting with our environment, and we took systems that you can describe by what is called a Lindbladian. Okay. Well, what is a Lindbladian? Is the solution of this being equal to 0. This you can also message and put it into a polynomial form. As soon as you can put something in polynomial form, think of us, okay? So we arrive with our machinery, we auto-approximate, and you can apply things like this, okay? So this is what we did, and I will tell you something that we did very recently with Miguel. So we did, not Miguel Navasquez, Miguel Frias, who is a postdoc now in my group. And for instance, in that case, we found a way of finding, I have to go fast, also bounds for even for the thermodynamic limit of steady states. And I can say that here, the method works well, just for you to have a representation of things what happening for 2D. No, sorry, this is 1D. For instance, just to have 2D. I don't have time, okay? But, okay, you don't see, but the upper and lower bound are here, okay? So for 2D systems, these are upper and lower bounds on, say, magnetization, the direction for the steady state in the thermodynamic limit. Okay, so I would say that we are basically solving the problem, because you see here the gap between the upper and the lower bound is very small. Okay, I don't have time for that. So I think this is a problem that deserves investigation. I'm very interested in finding how these polynomial tricks can be adjusted to the many-body system. To be honest with you, it is true that in principle the method is scalable, but of course we are far from being as scalable as variational method. I mean, we are not the only ones doing these things, so there is also papers by the Fosis, by Norbert Schuh and Miguel Navasquez and co-workers. So I think it would be nice to see whether we can do these things really competitive, okay? And because then we will have some sort of form of certified many-body physics in which you can derive rigorous predictions in the terms of bounds for many-body systems in a scalable way. Okay, thank you very much.
Wonderful. Thanks for this great talk. There's questions, yeah.
Cool stuff. You know, I like it. And while you gave the talk, I was just thinking, a very nice property that the ground state must have is that the variance of the atom is 0. And this gives you an additional polynomial concept.
Yes. No. Miguel has papers on these things where, you know, usually the solution of SDPs satisfied some extra optimality conditions, and he was exploring these things together with Mateus, Araujo, and co-workers. And the main numerical person in our paper was G1, who was a postdoc in the group of Victor Magron. I believe in the first version of the paper, he didn't do that. Then he included these sort of extra conditions and didn't find a big improvement. But I think one of my hopes in reaching making methods more scalable or closing the gap is trying to use more information about the physical system, like the variance has to be 0. Well, I mean, I think there is room for improvement, I believe, trying to understanding the physical properties of your system. Yeah, I think it's worth considering. Yes.
Another question? Yeah.
What do you mean? Like, well, okay, I cannot give you like, I think you can compute things, no? So in the variational methods, if you use say a matrix product state, you know how things scale with the bond dimension, and it's, I don't know, like if it's 1D is n times chi square times the local dimension. Okay, well, there is an expression. And in our case, when I say scalable, you know the SDP's hierarchies. If you fix a given level in the hierarchy, the effort with the number of particles grows polynomially, and you can also compute the polynomial in system size for a given level. Okay, so in this sense are scalable. So what I mean by scalable, perhaps let me just say also about scalability. So variational methods like MPS are scalable in the sense that if you fix one dimension, the effort scales polynomially with system size. Okay, of course this doesn't tell you that the error remains in your approximation remains the same. Okay, so since the problems are NP-hard, what this means is that to keep the error within a given approximation, you will have to scale the one dimension with system size. So the same is going to happen with our method, okay? So you will fix a given level of the hierarchy for the experts. Probably you will have to increase the level for large system sizes. But if you keep the level, things are scalable.
Can I follow up on this? Like a few years ago, I did a little mini single author paper on like how good these approximations are, like the Anderson bound, your bounds, and so on, that they're guaranteed to be constant in the, like as an energy density, so that you get an a priori guarantee in how good they, how well they must work. Do you have like guarantees of that type also for these other methods? Because you could say I get an upper and lower bound, but I'm guaranteed to be like within a constant error in like per side. Also, that must be true, but you haven't looked at this.
We don't have anything.
But maybe that's interesting. Yeah. There was another question here.
Related to Richard's question, if you try to minimize variance in terms of energy, could you target excited states?
Not at the moment. So I don't know how to do it. No. Yeah, I think.
You can do it by
well, me, I don't know. Miguel may know. Okay, so yes. Well, I think something that is also interesting. Okay, there are two. You might have two things. Do things scalable, so you go to the condensed matter community and people don't make fun of you. Like, okay, because I think here with our paper, this guy G1 reached 2D system the size 16 times 16. I think it's not bad. Okay, and the other thing which I also find interesting, more on the mathematical physics, is give me a many-body problem, try to put it in a polynomial form, and then you have all these certification guarantees. And for instance, Miguel has a very nice paper on dynamic evolution, and he managed to put the exponent of the dynamic evolution in applied these sort of ideas, okay?
That was the last question, but let's have Ulrich already set up. You're the next, right? Set up his computer, and then while he's setting up, we can take the last question that was here, yeah.
How's the convergence scale with like the samples of the sample space? And does like the observable nature change its convergence rate?
The what, sorry?
How does the algorithm converge, like the convergence rate? And does the observable happening change very much its convergence rate? Like polynomial exponential?
Okay, so I think if I think about non-commutative polynomial optimization in general, okay, without any reference to any many-body system, okay, this does not converge because our motivation came from quantum correlations, and it has been proven that there are problems that are Turing undecidable. Okay, so you won't get any convergence rate. Now, here we know that since it's a qubit system, there are some. We know that we converge in a given size. About rates, I'm not aware of any result about how it goes with the.
Wonderful. Thanks again for the great talk and the great discussion.